First, we have 1,000. So if you take 10 times 10 times 10, you get 1,000. It's effectively, like we talked about with scientific notation, it's 10 to the third power. So what comes to your mind when you think thousands, Matt?
Thousands is, you could order thousands of something off Amazon. You could order 1,000 toothpicks on Amazon. If you spill them on the floor, you could swipe them up and you'd be annoyed you did it, but it's a task you could get done. So
True.
thousands is a quantity, is a household quantity within reason.
Very true. Yeah. And also some major cities around around the world, like Pittsburgh, Denver, Seattle, those are measured in thousands. I think Pittsburgh's around 300 some thousand. I could be wrong, but it's definitely a major city mark for sure.
Population of Iceland, about 350,000. So
beautiful, beautiful.
Yeah.
Oh, there's also 86,400 seconds in a day. And if you're in engineering school, I had to use that conversion a lot in like fluid flow and chemistry, because you would have to get these flow problems in liters or gallons per day and have to convert it to another type of volume per second. And that's especially like involved with river or dam flows, and it could also possibly be like wastewater treatment. So it's definitely prevalent, especially for if you want to know some cool earth science. The earth is roughly 4,000 miles in diameter on the equator. And if you're standing at the equator, you are actually rotating at, or your tangential velocity is roughly about 1,000 miles per hour. So if you do the quick math, knowing the radius of the earth and the circumference formula, that's exactly it. So that's why space agencies, in each country are as close as they can be to the equator, so they can use that rotational velocity to escape this rock.
Yeah. Another actually pretty impressive number that can be expressed in only thousands is the number of kilometers light travels in a second, I believe. I want to figure out what's the speed of light in a second. Oh, yeah. It's about 186,000 miles per second.
That's it, miles per second. I know I was going to talk about that whenever we got closer to a billion. It's about 2.998 times 10 to the 8 meters per second. So
so it's nearing a billion meters per second.
Right.
Yeah.
But yeah,
a kilometer.
It's kind of a neat fact about our solar system. So if you take 1,000 Earths, you can actually fit 1,000 Earths inside of Jupiter. And then if you take Jupiter and you multiply it, if you have 1,000 Jupiters, you can fit 1,000 Jupiters inside the sun. So it gives you kind of a pretty neat scale when you're looking at the solar system that we live in. So it's pretty
cool.
cool.
A cool thing again with dimensions, because you say you can fit 1,000 of them in there, but it also means if you just wanted the width of the sun in Earths, I believe it would only be 100, because we're saying about a million Earths fit in the sun, but just the diameter, just the width from side to side, if you stacked 100 Earths end to end, that would just be the width of the sun. If you take it in all three dimensions, that would be a million.
Yeah, right. Ooh, that's really good. I like that. Well, speaking of a million, so a million is 1,000 times 1,000, which is kind of the same as taking 10 and multiplying it by itself 6 times, because as we talked about before, 1,000 is 10 to the third, it's 10 times 10 times 10. And then you multiply it by another 1,000, which is 10 times 10 times 10, you get 10 to the 6th. Hence why the numbers in the millions are labeled with 10 to the 6th.
Yeah.
So numbers in the millions, we see a lot in daily life as an individual. And we started off with thousands talking about cities. Let's talk about the largest cities. So the largest cities in the world are measured in millions, like Shanghai or Los Angeles, New York City, London, you name it. And heck, most countries' populations are measured in millions. For example, as of 2020, the US population, as I mentioned before, is 331 million people.
Whew. Yeah,
and counting.
People is a hard unit to conceptualize, because they each have a soul and joy and pain, and that's not as easy as building blocks.
Very true.
When you think about the number of people and thinking of millions of people, just astounding.
Yeah, I know some people that don't even like 10 people, just all depending upon your mood. That's a lot of people.
Oh, and another, I think, of millions we see on a regular basis is, I believe, a bit of information is it 1, 0, or O, or is it 8 of them? Is a bit just one binary?
Yeah.
Because then a
Yes.
bit and then a byte is are a bit and byte the same? Well, megabyte is well,
Megabyte.
kilobyte is
Mega's 10
1,000
to the
bytes.
6.
Megabyte,
10 to the
which
6.
is 10, yeah, that's millions. Megabyte is millions of units of data. And we
Right.
see a megabyte just on a selfie.
That's
The amount
right.
of information in a selfie you take is 1 or 2 megabytes.
Here's a pretty cool one. According to the Smithsonian Public Broadcasting System, and I also found it cross-referenced with Britannica, the earliest known evidence of hominid bipedalism was about 4.4 million years ago, which means that the earliest known ancestor of ours finally walked on 2 feet, and they're referred as Ardipithecus ramidus, which is pretty cool.
Ooh.
So just about 4.4 million years ago, somebody was walking like, I'm gonna start walking around on 2 feet.
Yeah, and time's also a really staggering example when you do big numbers, because
Right.
time, like speed, is one way. It's a one-dimensional
That's
entity,
right.
unless you're considering general relativity, in which it's intertwined with other dimensions. But time you can only move in one direction through time, so you can't stack hours side by side and build them up on a cube. You can only just go straight through it. No road stops, no bathroom breaks.
That's what I was going to mention, but I was going to mention it kind of on a pretty interesting aspect. So say if your kid's being really bad and you want to punish them, just have them go to the room and have them count to 1,000,000. If you do the math,
Right.
it'll take about 11 and a half days, and you'll get about 11 and a half days of peace and quiet.
Yeah.
Remember, if you break it down, right, I said a little
It's
while
only
ago,
11 days to count to 1,000,000.
11 and a half. Yep.
That's not bad. I
No,
might have guessed more.
yeah, it's actually not bad. You use that factor, like I said about earlier, the 86,400 seconds per day, and then you multiply
Mhm.
it out, and you get about a million seconds in about 11 and a half days. Yeah,
Huh.
yeah, yeah. More or less Earth facts. Somebody that really likes entomology. So the largest ant nest in the world had about 1,000,000 queen ants inside of it. And it's pretty crazy, right? So, and also
Yeah.
about 306 million worker ants. That's a big
Wow.
colony. Could you imagine just the volume of that
Yeah, it's like
colony?
working for a big company, just faceless. You're another drone.
Yeah,
Your boss
yeah.
doesn't even know your name.
Working for Amazon. Astronomy just ceases to amaze anybody. If you want to talk about big numbers, that's realistic in terms of like not looking theoretical. You get into
Yeah.
some crazy stuff, especially for the next category of numbers that we have, which is billions. Go ahead.
I found the data. I very much undersold it. The largest known star is 1,700 times larger in radius than the sun. So if you take 1,700 cubed, that would be the volume. That's how many suns we can fit in the biggest star. Which 1,700. Well, let's just round that down to 1,000. It would be 1,000 cubed is what, a billion?
Yep.
A billion suns can fit into the biggest star, and that would be off by. I mean, that's. I think you would have to multiply by another 5.
Yeah.
So
Right.
5 billion suns, just inconceivable.
Whew.
And that's nothing compared to the vast emptiness of space between those stars, which
Right. Right.
turns those gigantic behemoths into just dots in our night sky.
Very true. Very true. Holy man. That's exactly kind
Sorry,
of
we're
like
doing
what.
billion. I keep jumping from
No,
million
that's
to
great
billion.
because it just gives me a transition right into billions. So we've alluded that billions big, right? But let's kind of put it in perspective. So a billion is just 1,000 times a million. Or if you take 10 and multiply it by itself 9 times, you get that. So 10 to the 9th. It's also Carl Sagan's favorite number, billions and billions.
Billions.
Because I mean, billions are literally referred to as the astronomical subset of numbers. You see billions everywhere in the night sky. For example, there's an estimated 100 to 400 billion stars in the Milky Way galaxy itself. And then if you scale up from, so if you're talking about stars, which have their little solar systems, and then you scale up to galaxies, there's about 100 billion galaxies in the known universe. So yeah, it's pretty nuts. And we're going to get to that number later about, the amount of stars in the universe.
Yeah.
Common.
Another great fact, another good number, 100 billion, which is what, 9, 10, 11, 10 to the 11th power.
Yes.
Is that right?
Yes.
So that's the number of humans that have existed.
Yeah.
And about what, 8 billion of them are on Earth right now.
7.9.
Even though there's a lot of something like, I don't know if it's hit 8 yet. So maybe if we look behind some, closed doors and in closets, we can find the rest of them.
The census can't catch them all.
No, it cannot. But we think that might being such a big number, but most people, over 90% of people have already existed. So a lot of people have come before us, even though the population of the Earth is so much bigger than it's ever been. Even 100 years ago was maybe the 10th this size. Is that probably, it's exponential growth.
Yeah.
And again, humans are a thing I cannot scale down to a more conceivable notion, because one human being is all you really know inside the star dome that is your own brain. So.
Very true. Yes. And of course, our universe is 13.8 billion years old, dating back to the Big Bang, which birthed the many first, second, and third generation stars. Ours, particular, the sun, we call it Sol, is a second gen star, and the early solar system formed our planet Earth, which is about 4.6 billion years old. And we know that from radiometric dating rocks, and also some NEOs that fell into our lap. So
that's also interesting to me, that you would think the age of the Earth versus the age of the universe, that it would be some major factor, times E, but it's only 3 times, it's 1/3. Earth has been around for 1/3 of the time our universe has existed, since the Big Bang as we know it now.
And it's 93 billion light years across.
Right. It's going the speed of light in every direction, every moment we've existed.
Absolutely.
That sphere is getting bigger. A lot bigger. Multicellular, single-celled life. When did single-celled life appear? Was it 4 billion years ago or 2 billion?
It was about, I want to say about 4 billion. Man, that's
I think
tough.
it's 4.
There's a big time gap in which there's like beginning stages of life, which kind of form near the vents in the bottom of the oceans.
Yes,
it's gonna kill me. I can't remember.
I think it's. I'm gonna look it up really quick. I'm gonna talk while I do it. When did single-celled?
Is it 3.6?
When did multicellular? If I do multicellular appear? Oh, multicellular appeared about 600 million years ago. So
multicellular. So single cell. I think single celled. I think
single
is
cell,
like 3.6, 3.8. Yeah, in that range.
Yeah.
So
tough. I mean, in a grand scheme, it wasn't that long between Earth starting and life starting. I mean, it was a really long time. That's just those rounding errors between 4 and 4.6 billion.
True.
Long time. And then it took another 3 billion years before 2 cells looked at each other and be like, hey, you want to hang? You want to do our homework together? And then multicellular life proliferated, and humans haven't been around that long, but life has. I mean, dinosaurs 100 million years ago, 65 million years ago. But life's been around a long time. It took a long time for us to get Wi-Fi. You said humans maybe 100,000 years ago.
4.4, they started walking on 2 feet.
Okay.
Yeah.
All right.
Yeah. Pretty crazy. And that's hominids, not Homo sapiens. I can't remember about Homo sapiens. I think it's like 40,000 years ago. Neanderthals were still walking around, the last bits of them in Europe.
5 or 6 digits, I would say, in terms of years that humans have existed in a more modern form.
Right. Now, let me circle back. Remember when we were talking about time, it took about 11.5 days to count to 1 million. Well, let's scale that up to we're at 1 billion, right? So we'll just take about 3.5 months. It's about 3.5 months before your 32nd birthday where you hit your 1 billionth second. There's people out there that actually celebrate this. You can I would like you can celebrate your billionth second out of the womb.
I missed mine. I'm 33.
Oh, you just
I guess I'll have to wait around to a trillion. That's the next comma.
you want to wait
Better
32.
eat well and not drink if I want to make it that long.
Yeah, I mean, if you think about it, if you break it down in terms of days, that billionth second happens roughly on your 11,700th day, 11,700th day. And it's a factor of 1,000 larger because we talked about 11 and a half days, and then 11,500 days is your billionth second. So it's pretty easy to witness the difference in magnitude between a million and a billion. If you think about it, 1,000 times larger. That's massive, right? But let's jump up to the next scale, a trillion. So, or 1,000 times 1,000 times 1,000 times 1,000, 4 times. So, or 10.
Which is stupid because try and trillion is for 3.
Yep.
Which people may not know this. After a million, it starts going by numbers: billion, by, 2, trillion, try,
Right.
3. And then I won't spoil the next segment, but it's the number of commas minus 1.
That's it. Yeah. So a trillion is 10, but times itself 12 times, or 10 to the 12th. So right now there are about 3.5 trillion fish in the world's oceans, which is actually less than the amount of micro and macro plastics in the ocean. It actually surpassed it. Yeah, there's an estimated 5.25 trillion pieces of plastic in the ocean now.
Yeah, let's think about the 8 billion people.
Yep.
And you said 5 trillion?
5 trillion pieces of trash.
Let's round up to 8 trillion. So that's almost 1,000 Dasanis thrown out the window per person, or LaCroix cans. Yeah.
Yeah.
So it's not inconceivable to get to those numbers when you look on a per person basis.
Yes, that's exactly why whenever we were talking about trillion with the national debt, perfect way to do that, break it down into people. People can understand kind of people a little bit better. So yeah, I mean, if you're out there, surface fishing in the ocean, you have a greater chance of catching a piece of plastic than you do a fish for a meal.
That's depressing.
That is depressing. That is very depressing. And we talked about time. 31,000 years it takes you to get to your trillion second. So it's increasing by a factor of 1,000 again, just like about 31 years it took to get your billionth, 31,000 now to get to your trillion. So yeah, definitely eat right and keep exercising, Matt. You might get to it.
Well, if we unfroze a Neanderthal, they would get to say they're a trillion seconds old. 31,000.
Yes.
All right.
Yeah. All right. Well,
maybe one of the last Neanderthals. Yeah.
We got to find it. Okay. So the average human body has about 37.2 trillion cells, which of course runs in cycles. Researchers at Stanford University say that every 7 to 10 years, you get yourself a new vessel, meaning all your stuff gets traded out. Pretty cool.
Every 7 or 8 years?
7 to 10. Yeah.
7 to 10. Okay.
Depends on how big you are.
I have underwear older than that, so maybe I should tweak out my wardrobe.
No, it stands the test of time. They're like, Matt, we remember you when you were a young boy. Oh, and also the size of a cube of sugar, there is about 1 trillion bacteria just hanging out.
In it, not part of it.
No. Like if you took like the size of a sugar cube, there's about about a trillion bacteria in that small size. Yep. Size of a sugar cube.
I forget how small single-celled organisms are.
Yeah.
So
Microbes are
small.
nuts.
Which is weird because you can bust out a microscope in a middle school science lab and see cells.
Yeah.
And I remember seeing cells at this time that they were small, but they weren't that small. Because you'd look at them and then you'd look at it on the little petri dish with your eyes. You're like, I can see where I'm looking. I can't make out the shape of it, and you just put it under there, and you're like, oh yeah, okay, there it is. Yeah, I need a little assistance, but not that much. It's not like an electron microscope where we'll never have even a hope of seeing a molecule or an atom.
Special assistance we need from an electron microscope to see anything.
Yes.
Yeah, we can't use visible light at that point. Pretty cool stuff.
Yeah.
So here we have a quadrillion, right? That is a trillion times bigger than 1,000. or 1 with 15 zeros behind it. In scientific notation, that's 10 to the 15th, or multiplying 10 by itself 15 times.
Wow.
Yeah. So the first thing that kind of popped up to me whenever I was doing my research for this, so 100 quadrillion, that's the number of sounds and words ever uttered by humans that have ever lived.
Wow.
And counting.
I'm trying to picture a trillion with the scale I used before. So little centimeter cube, that's 1,000. So now a decimeter cubed would be a million. So that's 4 inches on each side. Now a meter, a box that's a meter wide on every side, that would be a billion. Trillion would be
1,000.
10 meters by 10 meters.
10 meters, 10 meters. Yes, right.
A 10 meter cube would have a trillion cubic millimeters in it. So that would be a big old box.
Right.
And now 100 meters cubed, which is a box that would sit on top of, that would squash a soccer field.
Oh yeah.
And if you think about just running, if that was just a big box of sand, of little cubic things, that would be, I guess, a quadrillion.
Yeah.
So it's a conceivable number. It's something we could picture. We could see the micro version and a macro version. The macro version would just be so darn big.
Absolutely. Ooh. Talked about black holes before. So just want to reiterate that there is an estimated 40 quadrillion black holes that are either roaming or at the center of each galaxy in the universe, which is pretty neat. Yeah. Super crazy. And a little over a quadrillion seconds ago, the dinosaurs were facing the KT extinction.
Wow.
Yeah. About 65 million years ago.
Wow.
So
that's pretty close. Yeah.
Yeah. Over a
only a million
seconds.
years off or so. Yeah.
Yeah. Pretty nuts. Little quick plug. If you want to learn about mass extinctions, check out the Earth's mass extinctions episode that we just did about a couple weeks ago. Very cool. Yeah. We talked about the KT extinction. Another good one on supercomputers if you're a tech person. So the Oak Ridge National Laboratory in Tennessee, there is a supercomputer there that runs calculations crazy fast, about 200 quadrillion calculations per second, which is about 1 million times faster than your average laptop. No, the next one is quintillion, excuse me. Quintillion's 18 zeros behind it. So 10 to the 18, or 10 times itself 18 times. So have you ever just walked on a beach and just wondered how much sand is there?
Yes, all the time.
So I did a little digging and did a quick calculation. One average beach holds about 1 quintillion pieces of sand.
Wow. So it's still a terrestrial number.
Yes, still a terrestrial number. Yeah. Something that you can kind of see with your own eyes. Yeah. It's beautiful. Here's some more Earth stuff. So the Earth is made up of about 97% salt water, 3% fresh water. There is about 353 quintillion gallons of salt water on Earth.
Wow.
Just imagine if we were actually using desalination plants across the globe, a third of the human population wouldn't have to face a lack of potable water.
That's incredible. I actually just took a screenshot on TikTok right before this. Here's a fact that isn't as useful as that, but or numerically useful, but there are 8 times as many atoms in a teaspoonful of water as there are teaspoons full of water in the Atlantic Ocean.
Yeah. Yes. That's exactly what I was going to get with a sextillion. So a sextillion is 1 with 21 zeros behind it. So it's multiplying 10 times itself 21 times. In 1 cup of water, there are more molecules in 1 cup of water than there are cups of water in all of the oceans.
Wow.
Yeah.
Molecules.
Yeah.
So now we're getting subatomic. Yeah. So I guess somewhere between quintillion and sextillion, we had to start using things that are smaller than we can see. But it's amazing it took us that long.
Yeah, isn't it?
We could still find. Yeah.
On top of that, so there are more molecules of air in 1 breath of air than there are breaths of air in the Earth's atmosphere. So with all the air that we breathe, the water that we consume, give it enough time, you've probably consumed the sweat of Cleopatra or the breath of Julius Caesar.
There's no way you haven't, because that's also because mixing becomes everything is mixing so well at every moment with water and air that
Yeah.
There's just, yeah, there's not a chance. It's like flipping a coin that many times. What are the odds that one of those quintillion
Ooh,
molecules hasn't been somewhere on Earth?
right. Right.
Yeah.
I guess it just shows how beautifully interconnected we are,
Yeah.
just through those examples. So I have a couple like real specific ones before we're done with this segment. And the first one that comes to mind is 8 times 10 to the 60th. So that's 8 times 10 and then 10 times itself 60 times. Yeah, go ahead.
Can I put that number in perspective? And actually, can I go on a little tangent here?
No, please.
So what was the last number we left off with? How many zeros was that? Sextillion, 18 zeros?
21.
21. Great. So a thing I want to bring up real quick is the Richter scale, which is similar to the decibel scale, and that it is a logarithmic number. Yes. Meaning that each number one, it goes up. Every time it's one bigger, it's actually 10 times more powerful in magnitude. We just measure kind of on a base 10 system. So my friend who has a lot of trouble with mathematics was saying, there was a devastating 7.5 earthquake. And he goes, yeah, well, we had a 5.5 here a couple of weeks ago and it wasn't that bad. It's like, yes, because even though it's only a difference of 2 between 7.5 and 5.5, that's 100 times bigger. And if you were to go to 8.5, that would be 1,000. So you look at like, a 9 and a 10, how much worse are they? 10 times worse. Imagine saying, oh yeah, we're not that far apart in height. He's only 10 times taller than me. So again, it's sometimes with this base 10 because, we think it's just, 1 unit bigger on the base 10 scale, or it's only a couple units bigger. So a 21 digit number like sextillion versus a 60-digit number is inconceivably bigger. It's that number cubed. Yeah. It's just unfathomable. Because even though we think 21 and 60, we have a concept between those two numbers, we don't at all. That's nowhere close.
As a human being, it's like, that's what I was saying, those cognitive limits. It's like, man, can we really conceive some of these big numbers? And it's not even, this isn't even close to as big as the numbers that we're going to talk about.
No.
So the smallest measurements of space and time are known as Planck units, formerly dubbed after the German physicist Max Planck. So how is this relevant? Well, when working with the early stages of the universe, just after the Big Bang, Planck time is very important when discussing the formation of the 4 fundamental forces of visible matter and discussing the grand unified theory, or GUT. So check out the 4 fundamental forces podcast that we just did to learn more about that. But this length of time to present day from the Big Bang is roughly about 8 times 10 to the 60 Planck time. So instead of using seconds, we're using Planck time. It's just a different way that physicists measure time to solve problems.
Yeah, cool. It's hard to, I'm not well versed in it. I just know it's the smallest unit of time you can actually kind of bump into. It's things don't really happen on a shorter time scale than that because it's the smallest wavelength. So you can also think of the amount of distance light travels in a Planck unit of time is a Planck unit of length,
right?
Which we might be seeing that one again. But that's the smallest. Things don't really exist below that because they exist in a probabilistic state between Planck lengths.
Right. Time in its most simplistic and smallest form. So here's another good one: 10 to the 81. So 10
again, 60 to 81. Oh, they're not that different. Wrong. So different. You could not see if you were happen to be able to look at 10 to the 81 of something. Right? If you could scale it down so you could just have it set it in front of you, something that was 10 to the 60th next to it, you would need a crazy good microscope.
Oh yeah. Yeah. So 10 to the 81st power, or 10 times 10, 81 times. That's the sum of all particles that make up the visible universe per astrophysicists' calculations. So if you took all the particles and started counting them up, 10 to the 81. I think 10 to the 81 is a little more beautiful. I saw 10 to the 78 to 10 to the 82nd. Per source,
right?
That's such a. I mean, how do you get that perfect? It's an approximation.
atoms in our galaxy is it's more than 10 to the 67th. I know that it might be the low 70s, and then the whole universe is only 10 bigger than that. So think about how much bigger our universe is than just our galaxy.
Yeah.
And then that's only a difference of 10, roughly 10 or so digits.
Jump it up 10 to the 90th. So building off the Planck measurements and the very first instances after the Big Bang, or the Planck era, the universe was so hot that forces couldn't coalesce to form matter. It was the universe's primordial soup, so to speak. And the estimated density of that time period is 10 to the 90, or a quindecillion. Quindecillion.
What are the units on
The
that
units
density?
are kilograms per centimeter cubed.
Wow. Even, I mean, what in this world is a kilogram per centimeter cube? That's a highly dense substance, because because water is, 1 gram per centimeter cubed, more or less how we made the scale.
Right.
So you need, again, that's another great thing to use for scaling weight with water, is
Absolutely.
that a cubic decimeter, so 4 inches cubed, would be 2 pounds of 2.2 pounds, 1 kilogram of water.
Yeah.
And a cubic meter of water is a ton, 1 metric ton, 2,200 pounds. So yeah, that's hard to push around.
that's an inconceivable number. All right, last but certainly not least, the Google. So one with 100 zeros behind it, or 10 times itself 100 times. This is where the company Google got the idea for the name. They took Google, the number, it was kind of like conceived in like the early 1920s, and they by accident changed the spelling. And it was just a hint that the large capacity of information that Google could contain someday.
Right.
A great example of Google is Hawking radiation, or the natural decay of black holes over time. One supermassive black hole, which is typically the size of a singular galaxy, takes about 10 Google years to decay. So, I would love to get into that with another show, because black holes are super fascinating, but I'll leave you off here with a teaser. But black holes do evaporate over time from Hawking radiation. But moving on.
Way above my pay grade. All right. I just like Google. I mean, I hate Google. There's things I hate, and like, it's one of 3 numbers that is a verb, along with 86 and 69. And what else do I like? Oh, it's funny because Google I'm blown away that you found a real life example of Google, especially in a non 3-dimensional one, but actually in a linear one, because time is linear. So I'm very happy to hear context for a Google number, even if it's still kind of inconceivable to me. Google is just, if you have to explain it to another species, no, it's a number of our fingers multiplied by itself, the number of our fingers times the number of our fingers. Yep. That would be it. So that's all it is. It has no mathematical, it's just kind of someone just decided to make a fun big number that's easy to write down. Yeah,
it's beautiful. I mean, 10 to the 100. Let's talk about the Googleplex. So that's 10 to the Google power. So it's 10
to the 100.
10 to the 10 to the 100. Really
another way of putting it is, it's a number starting 1 followed by zeros, and the number of digits is a Google.
Yes. So here's what's really cool, and it's really relevant. So we talked about the amount of particles in the universe, 10 to the 81st, right? So there's not enough particles in the universe to allow you to write out that number if you assigned 1 particle per 0. Yeah. Started writing out the Googleplex.
Just writing the digits of it
itself. Right.
If you took 1 atom per digit, you would still be off. You would still need 10 to the 20 times more. Yep. Which is what number was that? Sextillion. So if you had a sextillion universes, you would just barely have enough particles
Yep.
to then list the digits of this number.
Yeah. Yeah.
But I don't love that one because I can't think of a unless you have one, I can't think of a practical example of Google.
I can't.
Flex.
I can't. I just wanted to it was more practical towards the amount of particles in the universe. I just wanted to hit it up just one more time and say, this is how massive this number can be. And we just can't write it down we can't write it without running out of particles. Like it's nuts. Assign a particle to the zero.
I can one up that in the next round though with something.
I'm so excited. I can't.
Yeah.